I am screen sharing. I must start video. Start video. Oh my gosh, there I am. We have, let's see, 1, 2, 3, 4, 5. So we got 21 people at this point. Coming up on 50%. Not too bad. Oh my gosh. Now they're pouring in. People are pouring in. I love it. Oh. 60. Hello?
Hello. This call is from Law Enforcement Unit F, Federal Reserve System. We have found suspicious activities from your
can you guys hear this? I'm getting spam called on my stupid phone, despite paying for a stupid spam blocker.
In order to talk to an officer from Law Enforcement Unit
From Law Enforcement, blah, 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 blah. Yeah, sure. Right. Right. Oh, yeah. That sounds great. I'm just going to keep them on the fucking line. That's what everybody should do. Just keep them on the line as long as possible. They hung up. Goobers. Okay. So 1, 2, 3, 4, 5. We got 50 people. My God, that's like 99%. Amazing. So let's see. I wish I could see what you guys saw. I wish I could see what you guys could see exactly. That's all right. So I'm gonna wait here for a couple minutes because I have to wait for a couple minutes till it's 8 a.m. Elvin, how are you doing this morning?
I'm doing very good, sir. Thank you. How are you?
I'm good. Elvin, everybody knows I'm just a stupid white guy, right? But
nope.
What is your ethnicity?
Have you heard of Nepal?
Of course I've heard of Nepal.
Okay, cool.
Yeah, I'm from between China and India.
Absolutely. Yes.
Yeah. Oh my gosh.
It's a very small country. I think it's like 1/3 of California.
Oh, well, it's as countries go, that's, I don't know, it's not huge, but let me see, there's Nepal and Tibet, right? There's another.
Yes.
Do you guys have a border in common or no?
No, only with China and India.
Got it. Right. Okay.
Yes.
Yeah. So Nepal, you guys have a monarchy, right?
Yes, and Mount Everest.
Ah, that's right. Yeah. Oh my gosh. Well, I forgot your largest feature there. Oh, that's interesting. Oh gosh. Well, what brings you to California?
I have my cousins here, but the main reason I had to come here was for my undergrad.
Yeah.
Oh, nice. I finished my high school there, and then I came here. Came here in 2014.
Nice. What's your major, Alvin?
Biochemistry.
Biochemistry. Good. You're in good company. Got a lot of good biochemists at San Jose State. It's sort of like about 20 years ago, maybe 25 years ago, San Jose State decided to become a research institution, and and all since then we've just been hiring research.
Oh.
And in the last 10 years, oh my God, we've gotten amazingly productive, well-funded, just like crazy good biochemists here. So you've got a lot of good people with whom you can associate.
Cool, yeah.
Yeah, so hopefully you'll be able to do that as time goes on. Are you planning on going back to Nepal or?
maybe after I complete it, but I haven't gone back ever since I came here. It's
Oh
kind of,
yeah,
yeah, it's kind of
yeah.
like a different life back home, but here it's, I mean, we always talk like like my family, we always talk like, they always call Asian parents are a little bit different.
Oh yeah.
Yeah, they
You
call for
guys talk
every,
every day?
yeah,
Oh my God, I love it. That's
not
like my
only
wife. My
once.
wife, my wife's Persian, and oh my
Oh,
gosh, so family oriented. It's like a little tribe. I think of it like a more tribal culture.
yeah.
Anyway, I'll shut up now. Shut up. I got to get
No,
on
no.
with stuff.
All right, thank you.
Thank you, Alvin. Thank you.
Yeah.
Thank you. Okay, cool. Okay, uh, so I think where we left off, folks, last time was molarity and molality. Um, and I'm not sure if I did any calculations for you, but hmm, I think we're about foil 32 here. Um, so here's a good example of a place where we can start this. Molarity of salts in the sea. Test yourself here. Now, I have to say just one thing. Today is going to be a little bit like it's a bit of a grind, you know, because we're just going to be exercising some muscles that we started, building up in Chem 1A 1B. We're just going to exercise them, and basically that's it for today, you know. And then as we go forward, we're going to hit a few new concepts. Just a couple concepts today. Mostly it's just drilling. So let's see if we can do this experiment or do this calculation. Calculate the formula mass of calcium sulfate. What is the molarity of calcium sulfate in a solution containing 1.2 grams in 50 mils? And then follow-up question is, how many grams of calcium sulfate are in 50 mils? 0.086 molar calcium sulfate. So let me work on that then. So we're going to start with 1.2 grams calcium sulfate. Oops, SO4 there. It looks like SOY. And we're going to ask the calcium sulfate concentration. These brackets mean concentration, right? So you guys can see this joke probably. So first of all, we need to calculate the formula mass of calcium sulfate. Calcium SO4. What is wrong with you? Calcium is 40.078 grams per mole, 32.06 for sulfur, 15.999 for oxygen. And then we multiply this guy by 4. And then what we're going to get here is 40.078, 32.06, and 63.996. Right? Add these guys up, you get 136.13, and 40 are insignificant, then we carry them. And this is grams of calcium sulfate per mole, right? What we want to do is we want to calculate the molarity of 1.2 grams, right, of calcium sulfate. So to start this, I just ask myself, to what is the molarity directly proportional, right? So if we add more calcium sulfate, we get a higher concentration, right? That means that this starts in the numerator, amount of calcium sulfate, right? We take moles per liter is molarity. So moles of calcium sulfate 136.13 grams. And then what is it indirectly proportional? What other information do we have? I've got to put it up there. We got 50 mils. Okay. 1 over 50.0 mLs, right? And then we convert that to liters, right? We got 1,000 mLs. We get to cancel mLs per liter. And this all equals 0.1763 capital M per molar, right? So that's how we do this. This is the proportional part. This is converting it to moles. There's the inversely proportional part. Convert that to liters. We got moles of calcium sulfate per liter. Right? The next question is in 50 mLs of 0.086, how many grams of calcium sulfate? It's all the same information, right? We're going to start with the directly proportional part, which is 50.0 mLs of solution, right? And then 0.086 moles of calcium sulfate per liter times 1 liter over 1,000 milliliters, right? Because we're going to cancel these mLs, right? We cancel these liters. And then we got to multiply by the formula rate, 136.13. Moles of calcium sulfate. Right? And this guy equals 0.5854 grams of calcium sulfate. So this is the composition of 50 mLs of solution. And this is this is the molarity of X grams in Y mLs.
Professor?
Yes.
For the first one, I think maybe I missed this. The 50 milliliters that was given to us in the problem.
Yes.
Okay.
If it wasn't, then I messed up. I think it's in 50 mLs, right? And
okay. Okay,
also
perfect.
50 mLs. Excellent.
Thank you.
Yeah. There we go. Cool. All right. So I'll give you guys just a quick sec to catch up, and I'm probably not going to cover all my notes today, but we'll do molarity and molality and parts per million, and maybe a couple of limiting reagent they are gravimetric analysis. That's what it's called, gravimetric analysis. Try and fit in a couple of those guys. Okay. All right. So I'll publish all these notes, guys. You'll see on the web that I published all the notes for last time, and I put up the PowerPoints as well. So this is not necessarily needing to be right here, right now, nor keeping up 100%. So I'm going to go ahead and move forward. Okay. And let's go back to the foils here. And we can talk a little bit about percent composition. And there's basically two ways. You can mix them up, but that's pretty good. But weight percent is mass of solute over mass of solution. not solvent, but solution, right? This is just a total mass, right? So to do a weight percent, you might put in 10 grams, then add water until it was, 90 grams. And then the percent solid would be 10 divided by 90, right? And so that would be like 11%, right? Something like that. And then volume percent might be adding 10 mLs and diluting to 90 mLs, which means it would be 11% by volume, right? So volume percent is pretty weird. It's probably more like if you make alcohol solutions, like for spirits or something, you might use that. But we basically don't use it in this class. Well, we use it in 155, so might as well keep it in mind here. So here's a really common one, right? If you got 30% HCl, this is concentrated HCl, which, by the way, is as concentrated as it's possible to make HCl, right? 37% is you've got so much HCl in water that it's literally coming off as a gas. So if you open a bottle of concentrated HCl, there will be HCl gas coming out, and it is not friendly stuff. So please do that in the hood, or with abundant caution. Right? So 37% HCl. You want to calculate the density, or you want to use the density to calculate the molarity and the molality. Right? 37% is 37 grams of HCl per 100 grams of solution, and the density is 1.19 grams per ml. So you can go through this, and you can look at this calculation. The mass of HCl per liter so per 1,000 mils, right, is, oh gosh, this is so strange. So first you can calculate the mass of the per liter of this stuff, right? And that's 1.19 grams per ml times 1,000 ml is 1.19 times 10 to the third gram. So that's 1.19 kilograms, right? And then this, you multiply by the percent weight here, grams of HCl per gram of solution. And that gives you 4.4 times 10 to the 2 grams of HCl per liter. You've gone from grams per gram to grams per liter here. And now you just need to do the mole calculation. Bring this number down here, divide it by the molecular weight, and that gives you 12.1 moles, right? The molality is a little bit trickier here because molality is a weird unit, but it is used in industry, so we have to sort of contend with it. Molality is defined as moles of solute per kilogram of solvent, right? So it's like you weigh them out separately and you mix them together. And regardless of whether the volumes are additive, right? The volume could change a little bit when you mix them. Like you mix, 100 mils of acetone and 100 mils of water. The result is going to be about 190 mils, 180 mils of 50% acetone, because acetone and water, they kind of constrict when you put them together. But that being said, that won't compute into molality at all. Molality is like completely volume free. So what you need to do is you need to use the percent of HCl. Use that to calculate the grams of water that's in the solution. So in 100 grams, 100 minus 37 is 63 grams of water, right? So 63, if you move the decimal point 3 points to the left, 1, 2, 3, that's 0.063 kilograms, right? So, and then you need to calculate the moles of solute. So you divide that by the formula weight, 36.46, with 1.01 moles, right? So the molality is 1.01 divided by 36.3, and so so let's do this guy right here. What we're going to do is we're going to calculate the molality of 49% HF.
Professor,
Now,
somebody in the chat is asking you to go back on the page.
Oh, okay. Alrighty. Absolutely. So, thank you, Alvin. Yeah, there's a lot to kind of keep a handle on here. Yeah. There we go. Cool. There we go. So, so we're going to calculate the molality of 49% HF. Now, molality is it's going to be moles of HF per kilogram of solvent. Well, you're going to do molarity and molality. Molarity is moles per liter, right? So I'm just going to go ahead and dive in here. So we've got, oops. So we got 49% HF. This is a weight percentage, right? And we need to go to moles per liter. We need to go moles per kilogram of solvent. These are the two transformations that we need to have. So first of all, the formula weight of HF is 1.008 for H and 18.998 for fluoride. And together, these are 20.06 for HF grams per mole. And and also the density of this stuff is 1.16 grams per mole. And by the way, if you ever work with HF, it just loves to eat glass. It will just chew through glass like crazy. The first time I used it, I was just a stupid postdoc in a lab, and I thought, okay, I'm gonna pipette some HF out of this container. And I stuck a pasture pipette in, I pulled it out, and there was no more pasture pipette. It was like, oh my God. It was so crazy. So, let's see how we're going to go here. Let's go to molarity. We want moles of HF per liter of solution. So let's start with what we have. We've got 49 grams of HF per 100 grams of solution. And we're going to take that and multiply it by 1 mole. We've got to go from grams to moles, right? 1 mole of HF for every 20.06 grams of HF. Right? And then, so this gives us moles per 100 grams, right? And now we're going to go from, we're going to turn this 100 grams into a volume. So we're going to say, we need to cancel grams of solution. So we'll put 1.16 grams of solution over 1 milliliter of solution. Okay. And so now we got grams of solution canceling, grams of HF canceling, got moles per milliliter. Now we just simply have to convert moles per milliliter to moles per liter, multiplied by 1,000 mLs per liter. And then this gives us 28.41 moles of HF per liter of solution. And that is the molarity of HF, or HF in square brackets. Right? Now to calculate molality, we need the moles of HF per kilogram of water. Right? So this starts the same way. 49 grams of HF per 100 grams of solution. Right? 1 mole of HF per 20.06 grams of HF. Now this is going to give us moles per gram of solution, right? Now what we need to do is we need to calculate the grams of water here, right? So in 100 grams of solution, we've got 100 minus 49, that's this 49 here, grams of HF, right? Now this is going to go from grams of solution to grams of water, right? And we multiply by 1,000 grams per kilogram, right? And this guy here will equal 48.02 moles of HF per kilogram of H2O. And this is molal, is little m. I don't know if this, yeah.
We can see your notes.
Oh, you can't see them?
Nope.
I can see them.
Oh, okay.
I can see them too.
Okay, so maybe there's an internet connection problem there. I'm sorry, Mitra. We'll I don't know what to do about that. So, thank you for that feedback. This is like one of the big problems with the student online thing. Right? So this is how to calculate molality. It's sort of a pedestrian thing. It's really important to be able to not get flummoxed by it, like in a work situation or even an interview or something like that. Just to be fluent enough in this. So, can I move forward? So I'm going to go ahead and move forward, you guys. A lot of territory to cover here. There we go. So now there's this stupid thing about gold. It's not important. It's not on the test. It's cool, but like we just don't have time. So ppm and ppb, these are good to recognize. Parts per million is just the milligrams of substance divided by the kilograms of sample, right? So milligrams divided by kilograms, right? Or mass divided by mass times 10 to the 6. So, milligrams is grams times 10 to the third. Kilograms is grams divided by 10 to the third. So 10 to the plus 3 over 10 to the minus 3 is equal to 10 to the plus 6. So, it's parts per million, there's parts per billion. And let's go ahead and jump forward to the test question on this. The other ones are solved in the notes. But what they're asking us to do is to calculate the parts per billion into molarity. Right? Or actually, in this case, molarity into parts per billion. So, let's see. Well, let's go ahead and just do this guy. So we're going to get the parts per million of 23 micromolar. And this is a hydrocarbon C29H60. So I do not know what that's called, but it's a very long chain hydrocarbon. And it's just H and C. It's probably a petrochemical thing. So first of all, we need the formula weight. You've got to go from moles per liter to grams per gram. So moles to grams, we've got 12.011 times 29 plus 1.008 times 60, and that equals 408.799. Not all of there's only 4 sig figs, so these are the 4 significant figures there. So now let's go ahead and do this calculation here. We got 23 times 10 to the minus 6. This is the micro moles per liter, right, of C29H60. Right? Now we're going to take this and multiply by the molarity. We got to go from moles to grams, so that's 408.7990 grams per mole. And this equals 0.009402 grams per liter. Okay. We can multiply that. I'm going to put an arrow here because this equality is no longer going to carry because I'm going to multiply by another factor here. So 10 to the 3 milligrams per gram. I think it probably would. That equals 9.402 milligrams of this C29H60 per liter solution. Right? Milligrams per liter is identical to ppm for dilute aqueous solution, right? They should be approximately identical, but they are used identically in chemistry, right? So basically what we have here is 23 up here, so we get 9.4 ppm as our final answer. Right? And just to recap here, the ppm is identical to it's milligrams per kilogram, milligrams per liter in water. It's also identical to micrograms per milliliter of water. Right? And then parts per billion is, well, anyway, 300 parts per million, that's probably fine for right now. So, how are we doing so far? I've gotten through maybe a third of my notes here. And we are fully 60% through class.
Professor, what does the last like word under on the right for ppm on the bottom?
So microgram per milliliter.
Okay, thank you.
Yeah. All right, so I'm going to move forward now. Let's make some choices about what we're going to talk about next. Okay. Okay, so I'm probably going to try to get through the solution stuff, and I may leave the gravimetric analysis. I may leave you guys with a video. Yeah, milligrams per liter and milligrams per kilogram are identical. They're identical units, you know. So let's see. I'm actually reading the chat. So let's go down to 440. So okay. So this is just a very simple calculation of solution composition. If we have 16 millimolar copper sulfate, and we want to make another 16 millimolar copper sulfate, and we need to make 250 milliliters of it, how much anhydrous copper sulfate will we need to dissolve in water to do that? So, the way to do that is we're going to take the, we're going to make 250 mLs of the 16.0 millimolar copper sulfate solution. So, first of all, the formula weight of copper sulfate is 63.546 for copper, and then plus 32.06 for sulfur, and then plus 15.999 times 4 for oxygen is, so I forget what that is, but together these guys are 96.0560. And then we add these up. And this equals 159.600. The last couple of digits be fuzzy there. We're going to carry this to 3 sig codes. Right? So we want to make 16.0 millimolar, right? So millimolar is equal to so 10 to the minus 3 times millimolar equals molar. Right? So that is because you have a small number of moles, you've got a large number of millimoles. The millimoles are larger, right? So 16 times 10 to the minus 3 moles of copper sulfate per liter. Right? So we start this guy. And we're going to multiply that by 250 times 10 to the minus 3 liters. And then multiply this guy by 159.602 grams per mole. Right? So this is the volume, 250 milliliters is 250 times 10 to the minus 3 liters. So 1, 2, 3, that's 0.25 liters, right? 250 mils, 0.25 liters. 16 millimoles, 250 mils, times that equals 0.6384, insignificant, grams of sulfur. Right? So typically what you'll do is you will, if you have this situation in reality, is you'll weigh as close as you can get to 0.63, right? Or 0.64 here. And then you'll just record the actual weight. And then use that to calculate the actual concentration. That's just sort of a tip, for lab. But this is just how to get through this guy, right?
Professor Terrell?
Yes, sir.
On the left-hand side, where you have written 10 to the power negative 3 m equals to molar, isn't it supposed to be 10 to the power positive 3?
So let's say you have, it's just confusing, right?
Because
so I was like thinking about that. Oh, what is this thing? So if you've got like 1,000 millimolar, right? And so this is 1,000. Yeah, this is 1 molar, right?
Yes.
1 molar, right?
That's why that negative 3 should be positive 3. That's it.
No. See, because 10 to the positive 3 times 1,000 is 1,000,000. So you've got to take your millimoles and multiply it by a small value to get back to molar. Does that make sense? So if you want to go from an expanded unit down to a normal unit, right? This is the millimoles. It's a larger numeric value. To get down to molar, you got to multiply by a small value. And I'm just rationalizing here, but you'll find that it's actually true.
So the one that you have written on top left-hand side is 10 to the power negative 3 times millimolar equals molar.
Right. So this is the molar.
Oh no, I mean on the left-hand side, more top. That one. Yes, that part. Yeah, that part.
Yeah. Did you want to say anything else?
Yeah, I was just that number 10 to the power negative 3. I was confused on that. Only that one. That's it.
Right. I know. It's weird. It's weird. It's like a little minefield, right? But the millimolarity is 1,000 times the molarity. Right? I don't know. It's kind of strange, but trust me on this. Think about it a little bit, and if you
got it.
We can have a showdown next week or something.
Thank you.
I'm confident this time because I actually did the homework. So let's see here now. So here's just a simple solution calculation, right? And let's see here. So let's see here. So what if this is just from foil 53 of the notes. what if you have concentrated HNO3, and you notice on the wall that it says this stuff is 15.8 molar, right? And this is happens to be 70%. Right? This is another example of acids that are at their maximum concentration. Like HCl is like 16 molar, and it's just like maxed out. It's like outgassing HNO3. This is the maximum concentration of HNO3 that you can get, right? And if you want to take concentrated nitric acid and make 3 molar acid, and you also want to make 250 mils of it. So this is the final product, right? Then question is, how do you do that? How do you start this calculation? Well, we don't need the percentage because we're already in molarity, right? So what we can use is this simple relationship that C1 times B1 equals C2 times B2, right? And concentration times volume in molarity is moles. And that will equal moles of HNO3. And this is before dilution, and this is after dilution. Right? So it's basically, this volume here is often a pipette volume, and this is a vol flask, and this is a stock solution, and this is the diluted solution concentration. So, so this is basically just taking a little bulb of stuff, and you get it. This is concentrated. Then you add it to a bunch of water, a vol flask. And actually, it's kind of okay whichever way you do this, but typically what you do is you sulfuric acid is a little dicey, but you can go ahead and fill this like halfway with water. Then mix the concentrated acid into the water. And then H2O, mix it in there, right? And then add water to the mark. Bring it up to mark with water. And then you invert it 250,000 times. I'm just joking. You invert it like maybe 5 times. Basically, you have to ensure that it's mixed, and you can tell when it's mixed when there are no more Schlieren lines. Schlieren lines are like you can see things sort of mixing, you know. When you have a concentrated solution, and so how are we going to actually do this? We are going to take 15.8 moles of HNO2 per liter times V1 is equal to 3 moles per liter times 0.250 liters. Right? So V1 will equal 3.0 moles HNO3 per liter times 0.250 liters times 1 liter over 15.8 moles. Right? That's like dividing by this thing here, flipping it over and multiplying it. And this is C1, V1 equals C2, V2, right? C2, V2, C1, and then V1 should be liters, right? Yeah, so the V1 will come out of liters. So liters cancel there, moles of HNO3 cancel there, and then liters V1. It's going to be 3.5 times 0.5, something. I think it's
Professor, we can't see quite the bottom of it.
sorry.
No, thank you so much.
I'm like, I think it's like my stimulant's wearing off here. Because I did something different in my notes here, and I'm like, back and forth. So,
okay. We're all
yeah. Oh my gosh. So this is equal to, let me just do the calculation. Yep. So we've got times divide. Yeah, this is 47.47. Well, it's actually 0.04747 liters. And then V1 is mLs. We're just gonna move this guy 3 to the right. That's 47.47 mLs. And since we're working basically at 3 sig figs here, we're going to say 47.5 mLs. Oops. Okay, there we go. I think I got that on screen. Just and that is all the time that I have for today for the rest of chapter 1. So I'm going to put a video on for doing the gravimetric calculations. But honestly, you guys can probably get through them. If you need a fallback, you can look at the video, or you can just follow the notes on how to do the gravimetric calculations. Or you can say, hey, show us the stupid gravimetric calculations, and I'll do it. I'll just pay. So, any quick questions for me now? I'm going to be back online at noon for office hours. And then,
I have a quick question.
Yes.
In terms of the sampling, I know you haven't put any due dates because not everyone has access yet. I was just wondering, for those who do have access, where what progress should we be at this point?
You should be, you should have done the first one and be through the first half of the second one. But, really what probably, I'll set the due date for a couple weeks from now. So don't worry about it too much. But in terms of progress, you think about getting through the second homework set for now.
Perfect. Thank you.
Thank you so much. Awesome, guys. I will look forward to chatting with you very soon.
Thank you, Professor.
Thank you.
Okie dokie.
Thank you.
Thank you.
Thank
Guys.
you.
Awesome.